一些人。
Okay.
Okay, hello to everyone. Welcome to all of you to this session of the seminar in PDEs and Applied Mathematics that we are celebrating since 2020. Today we have the honor and pleasure to have with us Chi Wang Shu, a magnificent and experienced mathematician from USA. I will mention only some academic achievements about his long and fruitful career, but it is important to note that his work and achievements are more extensive than what I will mention now. With regard to his academic background, he obtained his Bachelor of Science degree from the University of Science and Technology of China in 1982 and his PhD from the University of California in 1986. He has been at Brown University since 1987 as the chair of the Division of Applied Mathematics between 1999 and 2005 and from 2023 until now. Now he is the Theodore B. Stowell University Professor of Applied Mathematics. His research interest includes high-order numerical methods for solving hyperbolic and other convention-dominated PDEs with applications in computational fluid dynamics and other areas. He is the chief editor of Journal of Scientific Computing and of Communications of Applied Mathematics and Computation. He also serves in the editorial boards of several other journals, including Journal of Computational Physics and Communications of the American Mathematical Society. And on the other hand, we can say also that he is a fellow of the Society for Industrial and Applied Mathematics, American Mathematical Society, and the Association for Women in Mathematics. Moreover, he received the first Fenkamp Prize of Scientific Computing in 1995, the Sayama ACM Prize in Computational Science and Engineering in 2007, and the Science John von Neumann Prize in 2021. He was also an invited speaker at the International Congress of Mathematicians in 2014. So thank you very much, Chi Wang, for having accepted our invitation to give this talk, and you can start when you want.
Okay, thank you very much for the introduction, and I'm very happy to give a lecture in this series. So today I will be talking about the high-order numerical methods for hyperbolic equations. Here is the outline of my talk. So I will first give an introduction, then I will give a brief comparison of several high-order methods, followed by one or two examples of recent developments, and then concluding remarks. So we are interested in solving hyperbolic equations, usually the hyperbolic conservation laws given by 1 here. So this is an equation in which u could be a scalar or a vector. If u is a vector, then f of u, g of u, etc. would be vector functions, and their derivatives would be matrices, the so-called Jacobians. So we would require that a linear combination Kc1 f prime of u plus Kc2 g prime of u plus Kc3 h prime of u, this linear combination of the three Jacobians with real coefficients should be diagonalizable with real eigenvalues and a complete set of eigenvectors. So this is an assumption for hyperbolic conservation laws. With this assumption, we still have plenty of applications, equations arising from applications which will fall into this category. The big feature of this, the main feature of this equation is that the solutions may be discontinuous. So you can have shocks, contact discontinuities, and so on, even if you prepare the initial and boundary conditions to be smooth and compatible. So the discontinuities will arise in later time, even if the initial condition is very smooth. Okay, so I mentioned that many applications will end up with PDEs, which fall into this category of hyperbolic conservation laws. This includes traffic flows, computational fluid dynamics, especially high-speed flows, electromagnetic waves, aeroacoustics, astrophysics, semiconductor device simulations, certain problems in computational biology, and so on. So in my own case, I have studied applications. I have been involved in applications in all of those areas, but mainly in the second one, computational fluid dynamics. In many applications, we also encountered the so-called convection-dominated problems rather than a pure convection equation, which would be here, ut plus f of ux equals 0. You could have a small right-hand side. Here, in this case, epsilon of au ux parenthesis x, so it's a second derivative term. That's a diffusion. However, usually we consider convection dominated to be the case where there is a small constant epsilon in front of it, which is small. For example, if you have compressible Navier-Stokes equations, but with high Reynolds numbers, then it will be like this. In that case, epsilon would be 1 over the Reynolds number. So if Reynolds number is high, then epsilon is small. Another example would be that the right-hand side could be, instead of a second derivative, it could be a third derivative, but still with a small coefficient in front. So this could arise, for example, in shallow water equations and so on. KdV equation, for example. For such convection-dominated problems, the main difficulty would still be the treatment of the convection terms. This is because when epsilon is small, even though the solution may not be technically discontinuous, the solutions may still contain sharp gradient regions. And if you are resolving those sharp gradient regions with a numerical method, with a mesh which is not so refined, then on your mesh, the solution will actually behave like a discontinuous solution. Hence, the difficulty would still be the treatment of the convection terms to control the behavior near those discontinuities. So that is why we will concentrate for the remaining of the talk mainly just on hyperbolic equations without considering the right-hand sides. Okay, so then after we have introduced the hyperbolic conservation laws, we are now coming to the concept of high-order methods, high-order schemes. High-order schemes are schemes which are high-order accurate measured by the errors. What happens is that if you, let's say you have a finite difference scheme, you have a mesh size h, then if you reduce this h, usually the error will also reduce for a good method. If you make h to be half of the original to h over 2, if the error decreases by also by half, then you call this method first order. If the error decays by 1/2 to the power 2, then you call this method second order. If it's 1/2 to the power 5, then you call this method the fifth order. Usually we call a method which is high order by some method for which the order of accuracy is at least 3. But sometimes even a second order method is considered to be high order. So anything which is not first order could be loosely thought of as high order. Now, would high order methods be beneficial for solving hyperbolic equations? Let's start with the simple, easier case, which is the smooth solution case. Even though I mentioned before that hyperbolic equations may have solutions which are discontinuous, but in some cases, for example, if you give a smooth initial condition for a short time, the solution will stay smooth. So in such cases, if the exact solution of the PDE is smooth, then there is a study to verify that high-order methods are beneficial. Beneficial is in the sense not only of asymptotic behavior. When h goes to 0, certainly high-order methods will be beneficial because the error decays faster than lower-order methods. But even if we fix h, if we fix the mesh size, you can still do a more detailed study. So this is carried out by the group of Kress in last century, that you can still quantitatively determine that high-order methods are beneficial in terms of reaching the same error level with less computational cost. Of here, how do you measure computational cost? At that time, it is measured by the number of operations. So floating point operations, like the number of multiplications and divisions and so on. So if you have a higher order method, it will reach the same threshold, viral threshold, let's say 0.1%, with fewer operation counts, hence smaller computational cost than lower order methods. This is especially true if you run it for a long time, if it's a time-dependent problem, if you run it for a longer time, and if you have a smaller error tolerance, let's say it's not 1%, but 0.1% error tolerance, then it will be even more apparent that the higher order method will be the winner. Okay, so this is for smooth solutions. Now, of course, I mentioned before that the solutions to hyperbolic equations may not be smooth. They may even be discontinuous. So for non-smooth or even discontinuous solutions, let's discuss this issue again in two different situations. We start with the simpler situation of linear PDEs. For example, Maxwell equations, linear aeroacoustic equations, and so on. So if your PDE is linear, even if the solution is discontinuous, is non-smooth or even discontinuous, we can still claim that higher order methods would be the winner. This time you have to be a little bit careful because if you measure the error in the usual strong norm, for example, L infinity norm or L2 norm, then it is not apparent that higher order methods would give you any advantage. This is because if you have a discontinuous solution, let's say if you have a finite difference method, you have a discontinuous solution, then at the discontinuity, usually the numerical solution will smear the discontinuity a little bit. So you will have one or several so-called transition points. At those points, the numerical solution will be order 1 away from the exact solution. So the error there will be order 1, not order h or order h to the power p. It's order 1. In that case, of course, if you measure the error in the infinity norm, you would not have any convergence because there is one point which doesn't converge. Then if you measure the error to be the biggest error all over the place, then it won't converge. If you measure it in L2 norm, it will converge, but it will converge in very low order, right? Because a single point will contribute order 1 error times delta x to that location. So if you measure errors in strong norms, you may get the wrong impression that higher order methods would not have any advantage in such cases. However, if you measure the error in a weaker norm, the so-called Sobolev negative norm, which is measured in the integral sense against the smooth functions, then you will be able to prove that a higher order method measured in those negative norms would still converge in higher order accuracy. This has been done for many methods, for spectral methods, for finite difference, for finite elements, discontinuous Galerkin, so on, by many authors. I mentioned some of the examples here, but there are many more. So if you can prove that the errors decay faster, decay in high order fashion in this negative norm, then you can design suitable post-processors which then can recover high order accuracy in strong norms, such as L2 norms and so on, L infinity norms, away from the discontinuity. So this is the reason that we say high order methods are still beneficial, are still of advantage for solving linear PDEs with discontinuous or non-smooth or discontinuous solutions. They are still high order accurate, but you have to be a little bit more careful in explaining what high order means in this case and how do you extract high order information in strong norms from the numerical solution. Okay, now let's come to the more difficult case of the solution of the PDE being non-smooth or even discontinuous, and the PDE is nonlinear. For example, we would have Euler's equations in gas, compressible Euler's equations in gas dynamics, and so on. Then in this case, things are more complicated because a rigorous mathematical proof of higher-order convergence, even in negative norm, is not available, at least not available for the general case. It's probably available for special cases, but not for general nonlinear PDEs. It is also true that many of the high-order schemes here I use unmodulated. For example, if you have spectral methods, you have high-order finite difference methods, and so on, with no extra treatments, then these methods tend to become nonlinearly unstable. What I mean is that these kind of schemes would generate spurious oscillations near discontinuities. These oscillations are with amplitudes which are order 1, and they do not, the amplitude of the oscillation do not decrease when you refine the mesh. It's only more concentrated near the discontinuity, but the amplitude of the oscillations are still big even if you refine the mesh. So what happens is that if you use such methods to solve nonlinear PDEs, let's say compressible Euler equations of gas dynamics, then, as I mentioned before, you would need conditions for those systems to be hyperbolic. You need conditions that the eigenvalues are real, eigenvectors are complete for the Jacobians. Now, this for nonlinear PDEs, this certainly depends on the solution. So, for example, for Euler equations of compressible gas dynamics, this is true. The system is hyperbolic only if density and pressure are positive. Now, density and pressure, of course, are physical quantities which should be positive. However, if you have a numerical scheme which generates oscillations, and if your exact solution has low density or low pressure regions, the density is already pretty small. And if you have oscillations, then numerical density could become negative, or the numerical pressure could become negative. Once this happens, then you are going into the non-hyperbolic regime. The eigenvalues will no longer be real. Then, of course, this is you post the PDE and the numerical scheme becomes unstable and then eventually blows up. So this is the difficulty. That's what I call the nonlinear. So solution becomes nonlinearly unstable, nonlinear instability, which is explained in this sense. So this is again a difficulty. So mathematical proof is lacking. That's one difficulty. And in a practical sense, the code may blow up. That's another difficulty, more serious difficulty. However, there are still reasons to believe that high-order accurate schemes, especially those modern high-order accurate so-called high-resolution schemes, which have nonlinear mechanism to control spurious oscillations, such as weighted essentially non-oscillatory schemes or discontinuous Galerkin schemes with suitable limiters. These schemes are still suitable choices for solving nonlinear PDEs with discontinuous solutions. This is, of course, I claim this, but the mathematics is still a little bit behind. So how do you justify this sentence that I just said? Well, you could say that these modern high resolution schemes, they do not generate spurious, at least they do not generate large spurious oscillations and discontinuities, hence they are called essentially non-oscillatory. So that would not bring you to the non-hyperbolic regime. However, you still need to prove mathematically that the method is really high order, let's say measured in some negative norm sense, but this is in general difficult. However, there is strong numerical evidence that I will show later that would justify this statement, namely the high order scheme is still beneficial for nonlinear PDEs with discontinuous solutions. I mentioned here that Lux has a paper in 1978 arguing that for nonlinear systems, high order information is retained by a higher order scheme and may be extracted by post-processing. His argument is in the information science sense, so it's not a direct proof. However, there is a strong, gives a strong indication that this might be the case. Let me show you a numerical example to demonstrate what I mean by saying that modern high-order schemes are still beneficial for solutions, discontinuous solutions to a nonlinear hyperbolic system. So here I will show an example that we use a high-order weighted essentially non-oscillatory scheme to simulate a steady state flow in a converging diverging nozzle. So this is Euler's equation, the nonlinear Euler's equations of gas dynamics in a two-dimensional but symmetric flow that has a solution which we can write down. So there is an exact solution to this problem, which is discontinuous. Then we can measure the error very accurately and see what happens to our numerical solution. So for this problem, the discontinuity is in the middle of the nozzle, and the flow comes from the left to the right. Now, before the flow coming from the left reaches the discontinuity, that part of the region is called the inflow region. That region, usually it's easier to achieve high order accuracy because the solution has not encountered the discontinuity yet. The more difficult region to observe high order accuracy is downstream of the discontinuity. So after the flow passes the discontinuity, reached to the right side of the flow, then that part, usually you observe low order accuracy. Because at the discontinuity, the numerical scheme will give several transition points that has large error, order 1 error, that tends to be carried downstream into the smooth region. So here we would want to see what we can observe downstream. That's the difficult region for this Wano scheme. Here is a table that we measure the error in a very strong sense. You see, we measure the maximum norm of the error for this numerical solution downstream of the discontinuity all the way to the discontinuity. So we include even the very first point to the right of the discontinuity in the error computation. So as I mentioned before, the numerical solution can have some transition points. So the very first point to the right of the discontinuity certainly has a very large error that you can see in this column. You can see that the error does not decay at all when you refine the mesh. Here it is the mesh number of mesh points. The error does not decay at all because the error is basically the error at the very first point to the right of the discontinuity, and it doesn't decrease. This is anticipated, expected. However, we don't know if the numerical solution has a good negative norm convergence, but if it did have a good convergence, then we can utilize a post-processor that I mentioned before. So we utilized one of such post-processors. I don't want to explain what this post-processor is, just to say that after post-processing, we are still measuring the L infinity error, the maximum error, at all points downstream of the shock, including the very first point to the right of the shock. And the error decays. You can see here when you refine the mesh, the error decays very nicely in a high order way. Right? So what this means is that we have strong reason to believe the numerical solution is still high order convergent in negative norm, because a post-processor, which is designed based on the assumption that the numerical solution has a high convergence rate in negative norm, this post-processor can produce a very nicely high-order convergent solution. Right? So usually we say that you cannot cook something without rice. So here the post-processor would not be able to produce high-order information if the original numerical solution did not have high-order information, right? It cannot generate something from nothing. So there's a good reason to believe the numerical solution actually did have high-order information hidden in some kind of negative norm, and the post-processor would then extract such information and give you this evidence. So this is a very good example to show that high-order schemes are still they still contain high-order information even for systems with discontinuous solutions. Okay, so this is the end of the first part. So basically, I would like to convince you, or at least try to convince you, that for hyperbolic equations, high-order methods would be a good choice. This is true for smooth solutions. This is true for non-smooth or even discontinuous solutions for linear equations. And for these first two cases, they are theoretical justifications and numerical evidence. And it is also true for discontinuous solutions of nonlinear PDEs, nonlinear hyperbolic systems. This last case is just justified by numerical evidence and limited mathematical justifications. So still need more work in mathematics for this last part. Now, suppose we agree that higher-order methods would be good choices for hyperbolic equations, then the next issue would be which higher-order method. There are many, many higher-order methods in applications, and we would want to discuss several of them. Now, if the solution of the PDE is smooth, that is the first case that we discussed before, then the foremost choice by people would be the spectral method, because the spectral method is most efficient among high-order methods. The order of accuracy is infinity in the sense that the error is smaller than 1 over n to the power k for any k, So it is even it could even be exponentially convergent for analytic solutions. Exponentially convergent means that the error is e to the minus alpha n, where alpha is positive. Now, e to the minus alpha, of course, is a number less than 1. Let's say if it is 1/2, then the error is 1/2 to the power n. What this means is that if, let's say, if I have an error which is 0.02 for n equals, let's say, 10, then in order to get half of this error, 0.01, for a first order method, I would need to double n, right? Because first order, you need to double the number of points before your error can decay by half. So for a first order method, if I have an error 0.02 with n equals 10, then I need n equals 20 to get an error of 0.01. But for a spectral method with the error being half n, then I would only need 11, right? I only need to increase n by 1 because it is 1/2 to the n. So if you increase n by 1, the error is already halved. So that is really dramatic comparison in terms of getting the error down, right? For example, you can assign this homework to students. You can give students a simple PDE, for example, variable coefficient hyperbolic PDE, and with the exact solution. Then let's say you run with a smooth initial condition. Let's say you let the students run several codes. One is the spectral method code, the other is a finite difference of order 2, and the other is a finite difference of order 4. With the same n equals 16, the spectral method, the error is already 10 to the minus 11, very, very small. But the second order method has an error which is 10 to the minus 1. Even if you increase the order of accuracy to 4, which by our standard is already high order, the error is still only 10 to the minus 2. So that means the spectral method is really the winner in this case. Of course, any a good method would come with strings attached, right? So spectral methods, they are nice, but they also have very rigorous conditions. For example, usually you would want to have periodic boundary conditions for Fourier spectral. And if you do not have periodic boundary conditions, you would need to use algebraic polynomials like Chebyshev or Legendre. Then the grid points are no longer uniform. You need to use special grid points like Chebyshev points or Legendre points for the method to be stable. But then in many applications, people want to use uniform meshes. They don't want to use things like Chebyshev points, which are very non-uniform. Then you could use the so-called compact schemes, which some engineers, some researchers call these methods spectral-like because they really give very small errors with a reasonably coarse mesh. But they are not spectral methods, they are finite order methods, but the errors are pretty small. So these are possibilities. Or another possibility is a spectral element, which means you break the box computational domain into several subdomains, and at each subdomain, you map the subdomain into a box, into a square or a box, and then you apply spectral method. But of course, if you do it this way, you have to figure out how the information is transferred between the subregions, right? If you cut the domain into some subdomains, in each subdomain you use a spectral method, then between those subdomains you have to glue them together somehow so that the global method is stable and also accurate. You could even say discontinuous Galerkin method belong to this class, because what you could do is that you could cut the domain, let's say, into 10 pieces. In each piece, you use a polynomial and you use a higher order polynomial in each piece. Hence, in each piece, it is a spectral method. But then you connect all these pieces by discontinuous Galerkin fluxes. So then you glue them together in a nice way that the method will be stable and then high order accurate. So this is when the solution is smooth. Now, if the solution of the PDE has discontinuities, then what do we do? Well, remember, we have those methods, spectral methods, compact schemes, and so on. Before, we have those codes which work nicely for smooth solutions. Now we are encountering discontinuous solutions. What could we do? The easiest way to do is to add a subroutine, which is a filter, filtering the solution. So the filters, there are various kinds of filters, and usually filters have some parameters in them. For example, exponential filter, for example, there are many filters you can use, but many of those filters have parameters to tune. So the advantage of this approach is that it's really easy for your coding because you only need to get a filtering subroutine and you add it to your original code. So you apply your original code for one time step or several time steps. Then you call this filtering subroutine. Then you continue the computation. So it's basically very non-intrusive, right? You don't need to change your original code too much. You just add filtering on. So this is the big advantage. A disadvantage is, like I mentioned, there are parameters. Usually, there are many parameters in those filtering, and you have to tune them. If you tune them correctly, the results are usually very nice. But if you don't tune them nicely, then the results could be either too dissipative, so you lose the power of higher order methods, or not enough dissipative, then the solution would still be oscillatory. So there's a balance there, and you have to tune, which is a drawback. Now, you could also use one of those modern high order, high resolution schemes. For example, the weighted, essentially non-oscillatory schemes. Now, I would not want to explain these schemes in this lecture. If you are interested in them, there are certainly many papers that you can read them. What I want to mention is that these methods have the advantage of being robust, usually with no user-tuned parameters, and usually they are very stable for even very strong shocks. So roughly speaking, there's still filtering in this method, but it's built into the numerical solver. So it is intrusive, right? I mentioned before that the filtering is not intrusive. You have your old method, the spectral, compact, and so on. You just add a filtering subroutine, and that's it. Here, you try to go into the spectral method, or you try to go into the compact method. You try to change the method itself in a way that it achieves some filtering effect. So roughly speaking, this is the idea. So if you do that, certainly it will be more intrusive. It will be more difficult to design, more difficult to implement, and more costly to compute. So the disadvantage is the computational cost. Because you have to go into the method to modify the method to achieve these purposes, the CPU time, the CPU cost is usually 4 to 10 times more expensive than a second order scheme, a pure second order scheme like last Van scheme on the same equation with the same mesh. So this certainly not to mention that the method is also more difficult to implement than the standard, let's say, last Van scheme. So this is the drawback. So the idea here is that you have to ask yourself, do I want to use such fancy methods? Now, I would say you want to use this method only if it is necessary. If your problem is not so demanding, a traditional method with some good filtering will already do the job, then probably you don't want to go into these more expensive alternatives. You go into those expensive alternatives only in situations for which the traditional method would fail. Would fail in a sense. I explain what do I mean. For a survey of Wayno schemes, you can see this paper. It's a survey paper in Acta Numerica. Now, I want to show here an example for which even though Wayno schemes are more expensive, they are still justified. So this is a case of shock interaction with vortices. So this is a problem from aeroacoustics. So if you have a airplane flying and then generate shocks which interacts with vortices, which comes from the tip of the wing, and then will generate pressure perturbations. These pressure perturbations gets propagated through the air and reaches the ground or reaches wherever the place, and that's what we hear, this big loud noise. If we want to study this, the structure of the shock interaction with vortices are very complicated. You can see here that these are the solution, and they look quite complicated. Now, think about this. I have this main discontinuity, this shock, and then I have some vortices, and they interact, they generate these complicated structures. If my numerical solution is oscillatory, if at the discontinuity, I have numerical oscillations, which are usually a fixed percentage of the shock strength, let's say 6% of the shock strength, and then these spurious oscillations will have an amplitude which is already bigger than the amplitude of those vortices. Then there's no hope that you can get the accurate description of what happens when the shock interacts with the vortices, right? Because the numerical solution also already have spurious structures, spurious oscillations at the same size or even bigger than the true vortices. So in this situation, there's really no hope that you can use an oscillatory method, even if it is high order, to study the physics of this problem. So then in this case, Wayno is really a nice choice. On the one hand, it is essentially non-oscillatory, gives you a very sharp and non-oscillatory shock transition. On the other hand, it is high order accurate, hence allows you to resolve the vertices and the structure generated by the interaction of shocks and the vertices to high resolution. So this one, these letters are some structures of those interactions. But anyway, the idea is that high order Wayne scheme really gives you a very good description of the flow feature in this complicated problem. So this is for later time. And this is a three-dimensional simulation of the same nature, the same three-dimensional simulation of the same nature. So for this type of problems, I would say that you would want to use the high-order Wayne schemes or similar high-resolution, modern high-resolution non-oscillatory type schemes, even though they are much more expensive than their earlier version than, for example, spectral method or Last-Winghoff method. Okay, here is the same simulation. So this is one type of method. The other type of method I would like to mention is the Runge-Kutta discontinuous Galerkin finite element method. Now, this again, I will not go into the details of the description of these methods. Just to mention that comparing with the Wayne schemes, which are finite difference or finite volume schemes that I mentioned before, here the method is finite element. The advantage is that it is easier to use for complicated geometry because these methods inherently are designed for non-unstructured meshes. So they can easily get high order accuracy when the meshes are unstructured. Well, before for finite difference, you need structured meshes. For finite volume, even if you could allow unstructured meshes, you have a costly reconstruction procedure, this procedure is very messy when you apply it to unstructured meshes. But here, in discontinuous Galerkin method, you do not need any reconstruction because the method is finite element. It involves the whole polynomial, not just the cell average of the solution. So there's no reconstruction involved. So the method has the advantage, as I mentioned, that it is good for general geometry, arbitrary triangulation, and it's also easier for boundary conditions, easier for adaptive computation, and easier for parallel implementation. Very good wave resolution capability. I will probably give an example later. And also many good theoretical stability results. The disadvantage of this method is that if you use the method per se to solve problems with very strong shocks, then there are still oscillations generated near the discontinuity. So you need something else beyond the discontinuous Galerkin to control spurious oscillations. Usually this is done by putting in different types of limiters. Even recently there are studies on using Wayne methodology to design limiters, but you do need some limiters. Or more recently, there is actually a approach to use some damping terms in the weak formulation of DG to control oscillations. But anyway, you would need something extra in order to control spurious oscillations when you are using DG for problems with strong shocks. Let me show you, I mentioned that this wave resolution capability is very nice.
Excuse me, Chi Wang, you
Yeah.
have 2 or 3 minutes.
Oh, okay. Yeah.
Yes,
Yeah.
you can continue.
Yeah. Okay. So we have this example of applying DG for wave resolutions. So you have this linear PDE, and then you have the solution, which is the second order on the left and seventh order on the right. You can see the seventh order, the solution even after t equals 100 pi, which is 50 periods in time, are still very nicely close to the exact solution. This is the 2D, is the same picture. And this is a variable coefficient case. It's even more amazing that here the solution is the level curve of phi equals u equals 0. You can see there are two curves in this picture. One is the exact solution, which is black. The other is red dots. You can see that they agree with each other very nicely at t equals 1, t equals 3, t equals 5, which is, you see, very complicated structure. This mesh is not very refined. It's 24 by 24 mesh cells with P4 polynomials, piecewise polynomials of degree 4. And after t equals 10, you unwind, you come back to the initial condition. You do see small errors, but it's already very nice on such coarse mesh. And it's the same thing for nonlinear problems. Since my time is running up, I will basically stop here and do not go into examples of recent developments. So in summary, basically, I would want to emphasize that higher-order methods are good choices for solving hyperbolic equations, hyperbolic conservation laws. This is true even if the solution is discontinuous. Then we discuss several choices of higher-order methods and their pros and cons. Finally, the conclusion is that if your problem really has complicated flow structure together with strong discontinuities, then one of those modern high-resolution schemes like Wino schemes, discontinuous Galerkin, and so on, could be a good choice for you. Okay, so let me stop here. Thank you for your attention.
Thank you, Chi Wang. For me, it was very interesting. I found it really interesting and very clear, where you were differentiating the advantages and disadvantages of all the methods. So I liked it. Very rich, and the examples of the end also very, very meaningful. So now we will give the opportunity to the audience to ask questions or any comment or any curiosity if they have. Juan has opened the micros also and the videos if someone wants to comment anything. Do you have any question? If not, meanwhile, if someone wants to, I have some curiosity questions, T1. Yes.
Sure.
Yes. First, you said that well, at the beginning, when you were introducing the one hyperbolic equation, on the right-hand side of the equation, there was a epsilon multiplying the third derivative, no?
Right, yes.
And I don't know this type of equations, but what is the reason why you multiply by an epsilon that is a small one, no? What is
Well,
the idea?
yeah, in physics, of course, you may or may not have epsilon being small.
Mm,
Now, what I want to say is that the techniques I discussed in this talk would apply to cases when epsilon is small. So
mm,
if in your application epsilon is not small, then maybe you need other types of numerical schemes because
yes,
then the right-hand side may dominate, right? So then it
yes,
doesn't make sense to say, what do you do for the left-hand side?
yes.
Not enough. You would need to treat the right-hand side nicely. Yeah,
Okay,
yeah,
okay.
yeah.
Yes, thank you.
Mhm.
Then, yes, you mentioned the Weber-Bauer post-processing, no, at some point?
Yeah,
The
post-process.
Weber-Bauer. You said, I think if I have understood well, that it's useful to recover point-wise high-order accurate numerical solutions, no?
Yes. So
What is that? Yeah.
assuming you have high order convergence in negative norms,
Mm,
then you can design post-processors which can then recover pointwise or in L2 norms, strong norms,
mhm,
high order convergence in regions which are not at the discontinuity. So away from the discontinuity. Let's
mm.
say your discontinuity is at x
Ah,
equals 1, then you can recover from 0 to zero point
mm.
0.9, let's say, this high order convergence.
Oh.
There are some, so I did not go into the details of those post-processes. There are some post-processes which are strong enough to recover all the way to one. So that is the case. I give an example, numerical example. Over there, I recover the accuracy all the way to the very first point to the right of the discontinuity. And that is a stronger post-processor, and you do have such post-processors. All these post-processors are based on the assumption that your solution is high-order convergent in negative norms. Without this, then of course the post-processor can do nothing.
Yes.
Yeah, yeah.
There is a question here in the chat. I don't know if you can read.
Let me see. Let me see.
Yes, by Hernán Oscar Cortés.
Where is the
Can you see the chat? It's
what
the,
what?
Yes, good afternoon.
here
Yes.
we have it here. Yes. Hello. Hernán.
Hi.
My question is about the full chain information that you speak with for
What for the
what is full information in the case the Schrödinger equation, for example?
what further information?
For the Schrödinger equation,
If
no?
you have when you change
Schrödinger
the
equation.
technique. Yes, when you
Well,
change the technique.
Yeah, Schrödinger equation doesn't belong to hyperbolic equation though. Right. Schrödinger equation is more dispersive.
It's different from what you have
It
proposed,
would
no?
not belong to the class of systems that I discussed.
Yes.
Although discontinuous Gaultian methods can still be designed to solve them, but that's a different story. This talk mainly I concentrate on hyperbolic things, hyperbolic equations.
Yes, thank you.
Yes, thank you very much. Thank you.
Sure.
Thank you. And the last question, Chi Wang, you said that when the higher order methods are used in filtering, you have to tune some parameters, no?
Yeah.
Have I understood
Most
this?
of the filters have parameters, sometimes not
They
just
have to be
one.
tuned.
Yeah.
Yes. And what happens if we don't tune those parameters? The things don't converge? Or...
Yeah, well, if you don't, so usually people will just tune the parameter once for one example and then apply it to all other examples.
Yes.
Then what people found is that often then for some examples, the filtering is not strong enough so that oscillations are still there, even though it's reduced a little bit, but they are still there. For some others, there's filtering too much. That means you actually see much smearing of the discontinuity. So it looks more like a low order method rather than a high order method. So you just need the right balance. Just hit the point.
Yes.
Which could be, but there are many people who have experience in such things, and when you tune those parameters nicely, you really get good results. Yeah. Yeah.
Yes, I thought that your talk was in general very rich, no, with many ideas and techniques, and so thank you very much, Iwan. I enjoyed it, even if it was a bit far from my knowledge, but I enjoyed it. Yes, thank you.
Yeah. Okay, great.
Yeah,
Thank you.
so I will finish.